All right, hey everyone, welcome to week 42 of Chill Kernel Hacking for Fun. This week we are continuing with Lab 4, and we're continuing with exercise 7, which I implemented last time and last week, but unfortunately there's at least one bug, which is making it not work correctly. So we can just reproduce that right now. And we can see that after the fork happens, the parent process never actually gets scheduled again. We only see these messages from the child. So that's what we're going to look into today. It's going to be another kernel debugging stream, which seems to be the majority of my streams these days. But that's just how it is. So this is the 17th and it's number 42. As a quick side note, I am currently trying to get a ticket for CCC, and so I'm going to be switching over every once in a while to check my queue status. We'll see how that goes. But yeah, I have like this curl command that's reloading the page. Yeah, but basically, yeah, so I'm trying to get a ticket to CCC, but otherwise, let's do some kernel debugging. What's up, Mice TY or Micety? Hello. Thanks for joining. I'm just trying to think anything else that's worth doing before we start. So here, as always, it's always good to review the state of the Git history. All I've done is in the working tree, I have a few changes. I'm just adding the dispatch for the various syscalls that I added last time, and I have a tiny commit that just causes the Dumbfork program to run when as the init process. Okay, so that's it. Actually, I guess I could make a commit for this. I mean, to be honest, these should probably be amended into the respective commits that actually do these things. So I'm just going to not care about that. I could try to amend that. I might get into Git conflicts. I don't really want to spend my time. Let's call this. I don't want to spend my time mucking with Git conflicts if I don't need to. So I'm just not going to. It's called dispatch for new syscalls. Oops. Yeah. What's up, Tier? I am working on this kernel that's a part of this MIT course. It's like the MIT. It's like the old MIT operating systems graduate level course. So that's the kernel that I'm doing. It's like a basic Unix-like kernel, although it has a bunch of simplifications. Okay, I think I can leave this as it is for now. So we have a relatively clean working tree. And I'm just refreshing my CCC ticket thing also. Yeah, relatively clean working tree. Okay, let's get into it. So first, we want to understand what is, I'm also going to clear out all my tabs from last time. Let's just clear everything out. Let's go to dumbfork.c. This is the user program that we are trying to execute. What does this program do? So here's what we see. We see a bunch of stuff, and then we see all these prints that say, I am the child, 19 or 20 times. And if we go back to the description of what should happen, it says, we have provided a very primitive implementation of a Unix-like fork in the test program. This test program uses the above system calls to create and run a child environment with a copy of its own address space. The two environments switch back and forth using sysyield. Parent exits after 10 iterations while the child exits after 20 iterations. So yeah, what's up, Bihan? How you doing? Thanks for popping in. Right, so we are seeing the child behave correctly. The child runs 20 times. The problem is that the parent, we don't see any of these parent messages at all. And that means the parent is not really running. And that's something to figure out. Yeah. Okay. Sorry, I'm still a little bit distracted because I have my CCC ticket. I'm monitoring my CCC ticket queue. And I think last time I didn't get a ticket, and after 15 minutes it told me, but yeah, I'm just monitoring this thing. Anyone else trying to get a CCC ticket right now? Yeah. Okay, but so how do we begin to debug this? So the problem is that the parent process doesn't run. So what happens to the parent process? Like, what happens here? One thing we could do is add some more print statements here. Such as like Dumbfork. We certainly get to here. I mean I wonder if cprintf child exofork. Oops. Parent exofork. I wonder if this works. I also wonder if it's because I'm running with 2 CPUs. What about 1 CPU? Even on 1 CPU. Okay. So that is already kind of interesting. We can see that I think the parent literally just never gets scheduled again. Parent never gets here. Yeah. That's what it would indicate. So what? Could be the problem. So we see 1 child exofork and then I am the child. We do not see this at all. Let's go into sys exofork. So this is the libc. syscall.c. So here we are in exofork. So obviously, I'm just going to add more prints, calling exofork, rets exofork. Calling exofork. This thing, new env 1001, red exofork, child exofork. So this, I'm just gonna take a picture of this. Alright, somehow the perspectives got all messed up and we're like super huge. Alright, let's zoom in. Debugging why parent never runs after exofork. So again, after exofork. Okay. It says exofork. Env alloc. So we allocate a new environment. Oh, okay, so something's kind of weird here. This is where the print for the new environment happens. So the new the environment, so the child, something is super weird here. It seems like something is flipped around. Oh man, sold out of tickets in this pre-sale round. Bummer. Yeah, I don't know if this is a bit disappointing. I don't know if anyone else was trying to get a CCC ticket, but yeah. If anyone is able to get me a CCC ticket, that would be awesome. Because I'm not sure I'll be able to get one. Okay, now we can now I can focus full time on this. Yeah. Okay, okay, for real, let's get into this. So here's what's supposed to happen. So parent exoforks, child is created in non-runnable state. Parent continues execution and explicitly marks the child as runnable at a later state. What we're seeing is the parent exoforks, child is created. Child immediately runs, parent never runs. So maybe, I'll get a new. Maybe I am misunderstanding something here. My instinct is to do this and then dump the environments that are there. Just checking on Twitter real quick. Okay, cool. So my instinct is to dump the environments. In order to see the state, like there should be two environments. One of them is the original one of them is the child. It's not runnable. Clone parents register state but make child appear to return 0. That's what I thought I did. Okay, let's take this really slowly. So this process exists. It does the exofork, which does an env alloc to create a new environment to run in. But it's like a blank process. I'm going to take a moment just to read about this again. Yeah. Sys exofork. The system call creates a new environment with an almost blank slate. Nothing is mapped and it's not runnable. The new environment will have the same register state as the parent environment at the time of the exofork call. And the parent sys exofork will return the env ID I see. Return of the newly created environment in the child, however, it will return 0. Okay. Well, not actually. Okay. Yes. So that gives. Okay. The parent will return the env ID of the newly created environment. So envalc takes an env store and stores it in there. Right. Well, so what is this? Okay, weird. Yeah, I'm a little bit tempted to drop into the debugger to inspect this stuff a little bit more. But okay, I'm just thinking, because I want to make sure this is not failing, but what the piece of information I have weak understanding of right now is how this thing propagates back to the user. So the sys exofork function returns a value. And what happens there? So these things all just return this value. It's an int32. And trap.c uses that and sets the trap frame ret based on that, which is what I was attempting to do over here, but I think I did, but mess this up somehow. Because it's kind of like all about what is returned by this function. So it sort of seems like somehow something is returning 0 successfully. This is precisely if env_id equals 0. So the syscall, but the interesting thing is the syscall returns in like 2 places. It should be left as env created, except that the status set to env not runnable. And the register set is... I see. Oh, right. Okay, so in the syscall handling path, the parent does the syscall, we drop into the kernel, we start running this code. We allocate a new process, which is kind of blank. We tweak it a little bit. We set its state to be not runnable. And then we copy the trap frame, which I believe this is the right way to do that. And copy the trap frame into the child environment, which means that the child environment is now going to inherit the same register states. And we give a slight tweak to the EAX register, similar to what we do here, to forcibly make it return 0. Whenever this process happens to drop into user space, those are the register values that will be used. But then we physically return the new env_id back to the caller, which eventually flows into here. Which means the parent process should have a return value of like non-zero. New env_id was 0. Oh, that's the bug. Wow, that's the bug. Yeah, env_alloc doesn't return the new env_id. It returns a error code. All right, time to rename this. I was reading a bit of the OpenBSD source code, and they have this particular way they name things and stuff. Oops. And I'm going to follow that. So I'm going to call that error, which makes it very clear that I need to be returning env_id. That's the problem. Let's try it now. Yes, I think this worked. I think that was it. That was like the only issue. I was accidentally returning the error code from the allocate, like the env_alloc function, as the environment ID, but the error code is not the environment ID. It's just a 0 or a negative value, and it happened to succeed, which produced 0. Um, hmm. Yeah, I mean, I could even add an assert here if I felt like it. But no, I don't think that's really necessary. So that's the bug. And now it totally works. That's awesome. We see the return value is like some environment ID, and then we're in the parent, and then the parent runs a bunch of stuff, and then the parent activates the child, and then they seem to swap, and the parent should run 10 times, and the child runs 20 times. Okay, awesome. That was a lot easier than I thought it would be. Pretty simple issue. Luckily, no super hardcore stuff necessary. We'll get rid of this. And yeah, let's commit this. I'll actually amend this into sys exofork. And then we don't need this anymore. We still have that. So nice. I'm going to call that a win. If anyone's in the chat, I would love to get some W's in the chat, please. But yeah, I'm going to call that a nice, easy win to start off the day. And our exofork is working. So I'm going to take a timestamp note of that. Wow. What time? Yeah, thank you, Canada Honk. What time are we at? We're at 27:16. 27:16 fixed exofork bug. It's huge. Okay. Sick. So let's keep going. Okay, so I've done exercise 7. Be sure to check for any invalid system call arguments returning e-inval. In that case, test your kernel with Dumbfork and make sure it works before proceeding. What git TUI was that? It's called lazy git. Yeah, I'm a pretty big fan of it. It's pretty powerful. Challenge: add the additional system calls necessary to read all of the vital state of an existing environment as well as set it up. Then implement a user mode program that forks off a child environment, runs it for a while, then takes a complete snapshot of the child environment, runs the child for a little longer, and finally restores the child environment to the state it was in at the checkpoint and continues it from there. Thus, you are effectively replaying the execution of the child environment from an intermediate state. Make the child environment perform some interaction with the user using sys, so the user can view and mutate its internal state and verify with your checkpoint restart. You can give the child environment a case of selective amnesia and make it forget. That sounds interesting, and I'm not going to do it because I'm not really doing these challenges. I'm just trying to proceed with the main work. Okay, this completes part A. Make sure it passes all the part A tests when you run make grade. and blah 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 blah. Okay. Grade lab 4, lab 3. Okay. Believe this is how I was doing it last time. I'm going to make grade how does grade work again? If you run grade, where's lab? Okay, whatever. Run, the grading script is just, yeah, so that's what I was doing. And as usual, I need to go and fix the bit rot. This should be Python 3, I think. Okay, right, I seem to recall that I needed to just comment stuff out. I'm just going to run this. It'll probably fail some tests, but we will see. Okay. Okay. Dumbfork, fault read, fault write. Fuck, fault die failed. Ooh, fault regs. But wait a sec. Are these? Okay, yeah, no, fault read. Yeah, no. These are not, like, I haven't done this yet. So far, the only thing that should pass right now is test Dumbfork. And that somehow those other ones passed also. But the only one that should pass right now is Dumbfork. I also just remembered I forgot to ping in the Discord that I'm streaming, so I'm going to do that real quick. Yeah. Really quick ping. Okay, cool. So I think I'm in a good place. I'm successfully passing part A. Okay, good. Let's go. Let's keep it going, but let's take a 20-second break to stand up and stretch. All right, be right back. Okay. So what's next? Copy on write fork. Copy on write fork. Okay, part B. Or is there anything I should commit? I will, or script. And disable running unit tests and run Dumbfork as init. Okay, cool. Now we're in a good state. We can continue. As mentioned earlier, Unix provides the fork system call as its primary process creation primitive. The fork call copies the address space of the parent to create a child. xv6 implements fork by copying all data into new pages. This is essentially the same approach that Dumbfork takes. So it seems like it doesn't implement copy on write. But that makes me realize I don't actually understand Dumbfork completely. So it's a fork implemented in user space, but specifically, how does it work? So we have this Dumbfork. Dumbfork does exofork. Panics if an error happened. Otherwise, if it's in the child, it patches this global variable that's in user space to be correct. Yeah, so it slightly patches itself to fix up its state, and then returns 0 from this function. However, the parent returns and eagerly copies the entire address space. So this is the not copy on write thing. And it says this is not what you should do in your fork implementation. So, and how does that actually work? It needs to, like, I don't know, loop through the address space and copy stuff, I guess. And somehow it's able to do that. What is utext? It starts, so we have some like symbols here or something. End. R. Okay, I don't know what these are, but we somehow loop from utext to the end in page size increments. That's what a void pointer? You went 8T, okay. And then we dupe page. What is dupe page? Dupe page takes, what is env-id? Env-id is the child process's PID. So then we take that destination and we take an address, and I guess we just copy a page from that address, at that address, into the destination. And how do we actually do that? So we use these system calls we've implemented to allocate some memory in the child, map that memory as shared between, so allocate memory in the child, which apparently we can do if we're the parent, map shared memory between the two, or I guess map that page into our address space, this page map, and then do the copy using memmove for some reason. And it copies to utemp. I need to review actually what these system calls do. Okay. All right, so page. Page alloc allocates a page of memory in a particular process at an address with particular permissions. Okay, that's pretty straightforward. Page map a page at source to dest, and source comes first. So it's like a little bit confusing, but so from the parent's perspective, it's a dest, and we map a page of memory in the child at adder destination. Then we want to take that page and make it visible to the parent, and so that's going to be the source. The source is, in this case, the destination and the adder. That's in the remote, the child process. And then the destination, from this perspective, is actually us. And dest env-id, right? And it's 0 because there is this convention. I search for convention? Because there's this convention that a value of 0 means the current environment. So we're saying take that source page that's in the remote process, in the child process, and map it into the destination, which is us, at some address that's called utemp, which is like some temporary place in the address space. And we have some permissions. It needs to be, it's present, it's user space, and it's writable. Okay. So now we've established this remote shared mapping. The parent can access it. and we're going to copy in page size from adder into utemp in the parent process, but it's shared between the two. And then lastly, we unmap it just from the parent. So then it's only visible in the child. Yo, Afnan, what's up? I'm late side. No worries at all. How are you doing? Hope you're doing well. So that's the basic mechanism of how to copy a page into the child. It actually takes a couple of system calls to allocate the memory, make it shared, perform the write, which doesn't involve a system call, and then unmap things. And the also key important part here is that it's very important that the child is not concurrently trying to execute. So, and yeah, because otherwise it's like racy and stuff. So the child is like just paused, and we can do all this stuff and then explicitly mark the child as ready to go. And actually, fun fact, this is maybe maybe a little bit similar to POSIX spawn or something like that. I'm forgetting all the details, but I want to say POSIX spawn. Maybe just quick Google to see POSIX spawn. That whack. Yeah, it's like okay, this is like kind of detailed. Yeah, I don't know. There was something that jogged my memory, but I'm not going to look into it. So anyway, that's how we copy memory into. So we basically somehow we have this utext thing, which is where user space programs begin. So we're just kind of assuming that. We're just assuming that the program is loaded at a particular place, which is 2 times PT size. That's kind of interesting. We can read elf user Dumbfork very much got exams, so there's that. Hope you're doing well. Yeah, thanks a lot. Yeah, I'm doing pretty well too. But wait, but what? So these are the load commands that I'm seeing. But what? Page table size. Something like 4 megabytes, I think. Which is times 2, so 8 megabytes, which actually is this. Yeah, this is actually the 8 megabyte mark. So that's actually, it is the 8 megabyte mark. So for some reason, 2 page table capacities is, where things are loaded to, except for this like 2 thing, which I actually don't know what that would be. But anyway, okay, so basically we just have like basically this kind of guess at where our process is loaded into. And then we just copy, but then this end thing is actually kind of the interesting part. The end is like this extern like symbol, which I'm assuming comes from like some linker script from the user.ld, which is used to link user programs. Oh, and it's also this is why the programs, we can kind of assume loading place, because we actually hard code this into the linker script. Yeah. So that, and then we have this end symbol. So this is where that end thing comes from. So using the linker script, we can kind of broadcast information that's available for use in the C code about the memory layout that the linker specifies. And so in this case, we have this provide end symbol. And then in order to use that, we need to declare this extern variable declaration to indicate that it's provided by some other translation unit. I don't quite know how that works, but anyway, so we can get the end of our process, and we can loop through every single page from where we think the start is to where the end is, copy it. But that's not all. That's just, so there's also the stack. That is interesting. It would be helpful to reference the memory layout for this again. So yeah. So kernel space, user space, kind of ends at utop, and then everything below that is user space. We have this 800,000 number, which is where the program begins. And then there's like the normal user stack. I am trying to think of where that comes from. Who creates the user stack, actually? Like the stack is not in the binary, right? No. Someone else needs to be creating the stack. I wonder if it's in like this early libc code. Let's try to find this. Where is the user stack created? I think it's here. This is the code that I'm quite unfamiliar with. This is like the low-level user space setup code, and presumably it starts actually here at the start symbol. So this is where the kernel starts us when we are initially loaded into a new environment. The start symbol. See if we were started with arguments on the stack. So we're comparing. So is ESP at U stacked off? Then if it's not equal, then some arguments exist, apparently. that were like pre-pushed onto the stack, and ESP was manually adjusted. Otherwise, ESP is just simply set to the top of the stack. So if not, push some dummy things, and then call libmain. But who maps? Oh, right. So when we create an environment, we specify a bunch of register state, including pointing ESP at uStackTop to start out with. But someone needs to map. Someone needs to map that memory, and I think I'm just forgetting. Well, I'm not actually seeing it. Or is it somewhere here? Someone needs to map the stack memory. Maybe I wasn't patient enough. This is like libmain doesn't do that. All it does, I mean, we're already running C code, and so this is like kind of late to be setting up the stack. Okay, let's grep for uStack bottom. Okay, this is where it happens. Is it load iCode? Yeah, so okay, let's load iCode. So we create this kind of like, we allocate an environment or process that's totally empty. All right, be right back, 20-second break. So the general flow is we do env-alloc to create a new environment, but it's totally blank basically. Except that I think env-alloc does env-alloc, I believe, sets up the kernel portion of the user space virtual environment or virtual memory, but the user space portion is entirely blank. But then we call load iCode to set up the user space portion of the virtual memory, including loading the elf, but also critically the one other piece to this, which is mapping the user space stack. So actually, yeah, right. So that's how that works, which makes sense. Like, you can't, like, user space can't be responsible for making its own stack, really, because what do the first instructions do then if they don't have any stack to run on? I mean, they could directly make a syscall potentially, but I don't know. Yeah, no, it's just the kernel. Yeah, the kernel provides the stack here. Okay, got it. So back to Dumbfork. So basically here we're copying all of the stuff that we set up in load iCode, which is the pages for the process, but also the page for the stack, and we're assuming that the stack is one page. And but this is like kind of weird. So adder is just this variable. It goes to the end. Oh, I see. Wow. Okay, that's like not completely obvious, but it's taking a pointer to this stack variable and then rounding it down. It's completely arbitrary that it like the fact that they chose the variable adder is completely arbitrary. But that's like a little bit confusing actually because it almost seems to suggest that they're using the adder, but they're taking the address of adder, which is a stack variable, and then you take the pointer to that, so you get a stack address. Then you need to round it down to get the base of the stack. Interesting. That's not very intuitive. But yeah, what would a more intuitive implementation be? Like, at least, I don't know. I mean, there is a comment here, but maybe like some kind of dummy stack variable, just to make it more clear that the actual value doesn't matter. Anyway, and then lastly, start the in-child environment running by using this syscall with the env ID we got. And that's it. Okay, so now that kind of makes sense to me. So now the parent returns from this Dumbfork thing. It has successfully allocated using exofork, filled in the child manually, like by hand, like by duplicating pages, and then marked it to be in a runnable state such that it can now participate in scheduling. And then, but that doesn't mean the child runs though. That just means the child is ready to run. The parent still continues, and the parent will always be the first one to give this like print message. Well, we will always see an I am the parent first, because the parent will always return here and then come into the loop first and be the first one to do something before we hit the sys yield. So yeah, but then we hit the sys yield, and we will probably choose the child, and now we see the child, and then for right now it's very easy and deterministic, but these things just switch back and forth between each other because there's only two processes on the system, and they both yield and yield and yield and yield and whatever. But they're going to execute this differently because this thing is going to return differently. So if who has a value meaning against the parent, we get 10. Otherwise, we get 20. So, okay, got it. So now I understand the Dumbfork a bit better. Let's go back here. So xv6 does not do copy on write, apparently. Apparently, it copies all the data just like proactively. It's the most expensive part. However, a call to fork is frequently followed almost immediately by a call to exec in the child process, which replaces. I feel like this is POSIX spawn, and I wrote like a blog post on this at one point. Pitfalls with forks in real-time contexts. After calling fork, a parent process gets the entire address space write protected to facilitate cow. This causes page faults. On modern glibc, system does not use fork, it uses POSIX spawn. POSIX spawn doesn't cow. That's the difference I see. Public spawn doesn't cow. The parent and child share the same memory mappings. Yeah, they literally share memory. I mean, with regular fork, they initially share memory, but then any read on either of them triggers a page fault in either of them. POSIX spawn does a similar thing where the child is created and their mappings are shared. However, the parent is suspended while the child executes a short amount to reach the exec. And then from that point, there's no sharing at all. And so that's the similarity here. So POSIX spawn also has this behavior where one of the processes is suspended. Unlike fork, where you fork and then the child and the parent are both still continuing to be scheduled, POSIX spawn doesn't do that, and neither does this kernel that I'm working on. So yeah. So call to fork is frequently followed by call to exec. This is what the shell does. The time spent copying the parent's address space is wasted because the child will use very little of its memory before calling exec. That's the reason later versions of Unix took advantage of virtual memory hardware to allow the parent and child to share the memory mapped. Oh, what? Okay, yeah. So currently, I mean, we're not doing POSIX. Well, yeah, currently we're doing a dumb copy with this kind of implementation detail of like how we like one of the processes is paused in order to make that work for doing it in user space. But then now we're going to kind of level up one step and actually implement something closer to a regular fork, the traditional classic fork. Even though it has apparently all those problems that caused POSIX spawn. We're not addressing that here. Okay, so we're using virtual memory to share the memory mapped until one process modifies it. This is known as copy on write. To do this, on fork, the kernel would copy the address space mappings from the parent to the child instead of the contents of the mapped pages, and at the same time mark the now shared pages read only. So we copy these mappings, so the parent and child are now going to have the same page tables. And we also need to go through all the page tables and mark anything that is writable to be not writable and to rather be write protected. I don't actually know if it's necessary to even check. Like, it might be faster to just go through and unconditionally assign the write protect bit, but I need to refresh. Also, yeah, these frames are so huge. Oh, okay. Right, can't do that easily. These are the interrupts. Where? Okay, here. This is virtual memory land of the board. So we have all these bits. Format with 32 that page references a page table that maps a 4 kilobyte page. So we are interested, I guess. I guess it really is just this bit. Yeah, none of this. I guess it literally is the right bit. So we mark everything unwritable which is going to cause page faults if writes happen to them. And we can learn more about page faults over here, I suppose. Although not really. But yeah, 14 page faults. Yeah. I always get a little bit confused between general protection faults and page faults because they're kind of similar. Like if you access I don't know. Yeah, there's like certain conditions with the general protection fault, but maybe most memory operations produce a page fault if they're like invalid. I would need to look that up, but anyway. Right. Mark these read only when one of the process tries to write to one of these pages. The process takes a page fault. At this point, the kernel realizes that the page is really a virtual or copy on write copy. And so it makes a new private writable copy. In this way, the contents of pages aren't actually copied. This optimization makes a fork followed by, in fact, much cheaper. The child will probably only need to copy one page, its stack, before it calls exec. Okay, I actually just remembered that I have not run this yet on multiple CPUs, and I hope that works. Let's see. It didn't crash, so it seems like it worked. Let's try on. Well, I could, yeah, I mean, I could. I actually kind of wonder. What does multiple CPUs even help here? Or what even happens? I would imagine that the second CPU participates in this actually, but I'm kind of like not seeing the non-determinism that I'm kind of expecting. It seems to still be very structured and rigid. But another question would be, what would happen if I used 4 CPUs? And the answer is that nothing, like, I don't think anything really particular is going to happen there because we only have 2 threads running on the system. So we're only like at all times 2 of the CPUs will be idle. Well, let's see if it crashes. I don't know. It's not looking any different, even though we're seeing starting stuff. Click check if MP main is active. MP main should be active. And so it is. So these CPUs are like sitting there waiting for work if they yield. They are sitting there waiting for work. Although, actually, I think if a CPU enters this and cannot find anything to do, it will hit the halt, which actually halts the CPU until like an interrupt comes in or something, and I'm not really sure how set up that is right now. So it might be possible that the extra CPUs are just like hanging kind of dead a little bit, and I am kind of curious if we will see anything. CPU, oh wait, what? Oops. CPU num? Yeah. Okay. Yeah, so we're seeing something kind of like that, actually. We have 4 CPUs on the system, but all of them just hit the halt. And I don't think any of those CPUs are actually used really at the moment. I don't think they wake up. I think all of this is happening just on CPU 0. I am kind of curious how I would actually confirm that. And I think the way to confirm that is I can go into my trap handler. Oops. And I want to do something like putting a printf that shows the CPU number that we're on after all of these or something. Or I want to know... Or I want to know when we sched yield, maybe. I want to hook sched yield, I guess. I'll say something like running thread on CPU num. Something like this. Phase 2. Phase 1. So we're going to either... So now I've added these prints that are going to run whenever we pick a thread to start executing. These are the only 2 places where that happens. I guess technically even in env run I could have done this. Alright, but whatever, I'll just leave this here. And my theory is that we are only going to ever see the number 0 in the logs, because all of the other CPUs somehow just like get halted and nothing, and just don't contribute at all. Yeah, so this is approximately consistent. All right, 20-second break, stand up and stretch. Okay. I don't really think this is a bug, but I'm a little bit unsure what to make of this. Interesting. Trying to run Dumbfork with multicore produces very deterministic output. Too deterministic. For multicore. Seems like all other CPUs just get halted and nothing is ever run on them. Is this a bug? Not sure. Why can't the other CPUs get any work? I'm going to, so simplify this a little bit by just reducing it to 2 CPUs. Why? It's like, why can't... So I guess the answer is the parent process is the first one to run. It's running on CPU 0. All of the other CPUs have been configured to just kind of like block on this lock. And if the lock is ever free, they try to get some work from the queue, basically. So we start running the first, like the parent process on CPU 0. And that's like CPU 0 is process, the first process is created, it's the parent process. And we start running it on CPU 0. So CPU 0 is kind of busy. That's also the point where CPU 0 releases the kernel lock. When we drop into user space, that's like the coarse synchronization point. And so we drop the big kernel lock, which allows CPU 1 to immediately get the lock, because it's waiting there, spinning on the lock, trying to get work. CPU 0, the kernel, finally drops into user space, starts running the program. CPU 1 is like, yeah, finally I can immediately get the lock. And it goes and looks at like all the work, all the environments that are there. And it's kind of racing against the parent process. And what I mean by that is what happens is CPU 1 always wins this race and checks the environment list before the user space process has a chance to kind of like clone itself with exofork, do all the setup, and then make the process runnable. It takes a bit of time to do all this work in the parent process. And so while the parent process is running in user space and doing all these syscalls and all this stuff, CPU 1 just immediately wakes up, grabs the lock, checks the environments, sees that nothing is there, and just immediately halts and never wakes up again, because I don't think we've implemented that so far. And so when a CPU halts because there's no work to do, it halts forever, which means that from that point on, it's just like there's only one CPU there, and CPU 0 goes and takes all the rest of the work. And so I was mentioning all this non-determinism. We can actually observe the non-determinism, though, in the printing of these halting messages, because all of the CPUs are going to be contending on this global lock. And I would expect that on different executions of the kernel, we'll see different orderings of the CPUs halting. Let's just run it and see. So 1, 2, 3, that was the order there. Let's run it again. That was 2, 1, 3. So that's different, right? So that's an example of the non-determinism coming into effect, because all these CPUs, like CPU 0 drops into user space, releases the lock, and is busy for a while. All the rest of the CPUs immediately start contending on the spin lock, and that is going to be non-deterministic in terms of who actually is able to grab the lock out of all these CPUs that immediately start contending. So that's what we see, 3, 2, 1. So it's different every time. So the experiment I kind of want to do actually is I want to it would be interesting to make CPU 1 very delayed somehow. And so the parent process drops into user space and needs a lot of time to do a bunch of stuff. But what if we make it so that when the CPU 0 parent process drops into user space, CPU 1 can't get the lock still, like, for some time. And CPU 1 only gets to look at the envs after we've created one. Then I think that would be a bit of a different story, because then we would have two runnable processes in the queue, actually. And if we activate CPU 1 after that point, it can actually participate in things. So that might be kind of an interesting experiment to try, actually. Yo, Ismail, what's up? Nice to have you. Hope you're doing well. It's been going pretty well. Yeah, it's been a good one. I fixed this bug from last time pretty quickly, and now just doing a bit of explorations, I guess. Yeah, it's going pretty well. So I want to do this. I wanted to do this experiment. I'm not quite sure exactly how I would do that, but I think kind of. The main focus was implementing fork and like doing all this fork stuff, all this all these fork system calls, and I got that working. But I wanted to test it in multicore now, actually, because I was testing it with single core to keep it simple. But when I tested it with multicore, I noticed something pretty interesting, which is that none of the other cores are actually used. They just are just unused, and it's because they when the other cores wake up and finally get a chance to see if there's any work to do, there's no work to do, and they just permanently go to sleep. Because that's just how it works right now. And I want to make it actually so that all these CPUs can actually participate, and not just immediately see that there's no work and just die forever. I could add a syscall somehow. I don't know. So this is just going kind of off the beaten path here, but what I need to do is I need to add something else here that is just so this is the code that runs on the other CPUs, and they try to grab the kernel lock. And furthermore, I need to stop them until we can indicate that we're done here from user space. Buzzing noise from your mic, I think. Oh, interesting. Thanks for letting me know. I don't know. Hard for me to tell. Things seem mostly normal for me. I don't know if anyone else in the chat can weigh in, but thanks for letting me know. Yeah, I'm not sure what that would be like. I'm doing pretty much the same stuff as the last time. Okay. Hopefully it's not too distracting. So what I could do is I could add a system call. Yeah, I could add some kind of global state or something. Or maybe even another lock. There's the main lock, but then I have this other but I kind of feel like this exchange thing is the way to do it. Basically, I need to have, I don't know, some kind of like global atomic variable or something. And it's going to be initialized into some like waiting state. And it's going to like spin on that variable until it's different. And then I'm going to set it from a syscall handler. Interesting. 100% there on my phone too. It's a light buzz in the background. Thanks for letting me know. I wonder if there's something I can do about that. Light buzz. I think there's normally a bit of noise, but all right, thanks. I'll have to look into that later. Okay. The other like way easier way to do this is just to do like a stupid loop. I don't know, like 1,000,000 times. And the idea is just to make this thing like spin for a very, very long time until this thing can finish. But not too long. I want it to spin for long enough, for just long enough, where it's like this thing is like, wakes up, it spins for a long time. The parent process has enough time to get through basically here. It needs, or I could, I mean, I could use this system call also for this. You know what, this might be worth trying. Because, I don't know, yeah. This is a kind of a dumb idea. I don't know, but I could just like run this, I don't know. See if this changes anything. CPU 1. Just at some point, CPU 1 is not going to halt so immediately, I think. All right, maybe I need a much bigger number. So that, okay, that, is this right? Also, wait a sec, I might be overflowing. Okay, I might be overflowing the int. I don't know. It's still. Now it definitely hangs for kind of a long time. Okay, I don't know. This is still saying CPU1 halting so quickly. So it like hangs for kind of a long time, and then and then prints out like everything. It hangs there. Phase 1 running thread on CPU 0. That's so odd that this would block. You can't do usleep? I don't think we have a usleep. Yeah, I don't see a usleep anywhere here. I don't think there's any kind of sleeping code in the kernel. Oh, what's up, DeVito? Okay, I don't know. I kind of feel like, well, this didn't work, but I still really want to at least see the other CPUs used for something. All right, I'm going to briefly give this a try to implement this, like, I mean, it's basically another lock. But it's not exactly a lock. It's more like a condition variable. Okay, I just need to I need to have some kind of global variable that can be accessed. Maybe I'll put it right next to here. We have this kernel lock. Here we have it. It's this extern struct though, which is kind of interesting. Okay, I'm going to, all right, extern int, like quick lock or something like that. And I'm just gonna make it 0. Keep up the live streams. Thank you for the encouragement. So how does this work? So what is actually, wait a sec. So what is an unsigned? Okay, I'm gonna make it an unsigned also. Signed. Quick lock. Unsigned quick lock 0. And then this thing shows how to like do that. I'm going to, yeah, very much off the beaten path here for this kernel, but I'm going to do something like, oops. So here it is. It's like, while, oops. That's it. It's literally just this random variable. And because we have the header, we should spin long. We get it. We get access to it. That's our very shitty condition variable, basically. Okay. While this thing does not equal 0, what this means is like try to atomically put a 1 into the variable and return the previous value of it. Wait, no, this is wrong. I need to copy the unlock, which is this part. Which is just reading. Okay, yeah, so I'm being kind of stupid. So apparently I'm also gonna kill this palm tree. The holding thing, so I'm basically trying to, do this unlock part. No. Wait a sec. No, yeah, this is the part. We first try to acquire the lock, and it's basically spinning on the holding. No, wait a sec. Okay, I'm totally messing up. Spin lock is constantly trying to set it to 1. But, okay. But if it's already locked, it's going to be 1. And this thing returns kind of like the previous value of what the thing was. And so in the case that the lock is already locked, this thing is going to return 1. Even though we're setting a 1 into it, it's already 1. We're setting a 1 into like a 1, and so it's going to return locked. And that's not going to be equal to 0. What we want to see is that it was unlocked and we successfully put a 1 in there and the previous value was equal to 0. But while that's not true, we loop. So I do need this. And I mean, I guess kind of, yeah. So I'm trying to loop, and I'll just be like, while it's, I'll try to put a, okay, it'll be the same thing actually. So this quick lock thing needs to be initialized to 1, and it's going to be initialized to 1. The other CPU is going to loop on that and try to put a 1 in there, and change the state, which it's not going to be doing. And then in our syscall handler, we're going to release this quick lock thing and make it 0, which is going to allow this to succeed and hit the schedule, I believe. Okay, let's try this. Now I need to go to trap.c. and I need to go to set, like, or what, n, or what? Set env status. So the most important thing is that I make sure that I do this. Like, it's actually like a little bit sketchy, but like, I just need to make sure that I do this after this write, because as soon as I set quick lock 0, I guess I need, okay, now I guess I need this temporary spin lock header. All right, let me go to here. So how do you, so yeah, when you set into it, you just do the atomic set with the exchange. So this is my first time actually doing this kind of thing, but I think it might work. So basically, the idea here is I'm kind of conceptually releasing the lock, which is what happens here. Yes, exactly. It's the same kind of thing. We put a 0 into this thing. The reason it's a little bit sketchy, maybe, is because I'm really relying on the ordering here. I'm relying that this write happens first, and then the atomic write happens. Because if the other CPU, if this got reordered, which totally happens with atomics, if this got reordered, then I would do this. CPU 1 would like instantly grab, like go into the scheduler and maybe race against this write and actually still halt forever. So that's the concern. I don't actually think it's a problem because we're on x86, which is, what is it, like a strong architecture or something like that. And so by default, it has a lot of these strong orderings. But on a more weakly ordered architecture like ARM or something, you would want to be a bit more careful with this, I think. I'm also not totally sure with what semantics the exchange has, but I mean, this big comment talks about it. So I don't even know how I would use, like, how I would get into a situation where this is a problem. Because in order to do that, I'm thinking from C++, I would need to use the relaxed atomics or like the more like low-level atomic operation types, like the acquire and the release and stuff like that. But anyway, so this is my shitty lock, and I'm just gonna try it. What happens here? Okay, do I still? Okay, now it's deadlocked. Did I do something stupid? Yeah, no, it's interesting. This goes back to that mystery of why that super long loop was affecting the main CPU. So I tried to lock the kernel, so like this should just immediately like, okay, I'm just creating problems for myself. Running thread on CPU 0. Oops. What's the diff look like again? This thing. This thing. We have like the bad lock. Okay, I actually don't know. Something is going on here that I don't understand. I'm not understanding why the CPU 0 just gets blocked forever. Because I think it should be able to just continue executing. Phase 1, running thread on CPU 0. And then what? Like, so Dumbfork, for example. So, does this work? No. So now it looks like the process is not even starting on CPU 0. Which frankly does not make any sense at all. Like this lock thing. Wait, no. But it seems like, yeah, if I get rid of this, we should totally not deadlock or whatever. Yeah. So there's some weird reason that's maybe it's like obvious, but I don't see it right now. So it's nothing related to here. This is like the early boot up. And so this is just wait for the CPU to finish some basic setup, which it finishes here, and then the main CPU keeps going. So it's not like the main CPU calls MP main or something like that, which would make it subject to this. So now I guess the way to debug this, I want to find here, right? Oh wait, okay, wait. Maybe that makes sense. We unlock the kernel. This thing, yeah, okay, wait, okay, yeah. We grab the lock, we spin forever, and then the other CPU can never enter the kernel again because we've grabbed the lock, and then, yeah. So like classic deadlock. What do I do? Okay, maybe the way, okay, yeah, so I don't know, that explains it. That's actually kind of like pretty straightforward. I grab the lock, I spin forever waiting for this thing, but because I've grabbed the lock, the other CPU can never get it again. Maybe the easier thing is just to not do this, to not halt like this. Instead of halting, or yeah, at least instead of doing this, unlock kernel. We're going to unlock. It's actually kind of interesting how this works. I kind of feel like there should be a loop here or something. I mean, yeah, this is not really production code worthy, but like now I've added a loop where I've disabled this like dying behavior where if a CPU can't get work, it just dies. I've disabled that, and now I'm just making it spin. And so now we're like gonna have massive contention on the lock and stuff, but now what's going to happen is the CPU is just going to keep trying constantly to get work, and eventually the first CPU will finish and activate the second one and make the second child process runnable, and then this thing is going to have a chance to kick in, and we should see some things that are not zero here. Let's try it. Whoa. Kernel panic on CPU 121. What the hell? Okay, I'm going to delete. Okay, maybe none of these ideas were destined to work at all. Too bad. What? CPU panic? What about this? So now things are crashing, actually. Holy crap. All right, well, I totally failed. I completely failed at trying to make, like, enable the other CPUs to make them work through this fork example. Wow, what happened there? That, like, so much stuff just started to go wrong. Wait, what? Now, wait, how is this crashing now? What did I even do? Is it this? It must, be this. That's the only thing I've done. I've stopped doing the sched halt. Sched halt. Maybe there's something super important there. Wow. Okay, maybe it was a dumb idea to comment this out. That's crazy. Okay. I don't know. Wow. Okay. So let's just get back to a safe place. Okay. So this should be working again. Yeah, I'm not really understanding why. Cur env is the CPU local variable. Oops, wow. Seriously? Something about not halting these other... Really? Something about... Something about this doesn't work, and I don't really get why. First of all, why does that crash on one CPU? But it crashes after everything is done, which is interesting. 280, but yeah. It finishes everything, then like crashes. I have no idea where. That's the problem. I have no idea to really know where the crash is. Okay. Oh, I know why there might be some buzzing. My speaker is on. Just curious, Ismail, did that fix the buzzing? I just turned off this speaker that was right next to the microphone. Huh. But yeah. I don't know if I want to debug this, because I'm like creating problems for myself by kind of veering off of the path, and but I don't understand why or where this would crash. Maybe I will just quickly try to debug it. Okay, where am I debugging now? Because it, free end blah 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 blah. So that maybe it's gonna be very stupid. And destroy. I mean, I've. So we get past here. Okay. So now we're at the second one. And man, it would be so helpful to be able to print a stack trace on a crash, but I would need to implement that somehow. The best I can do is just kind of like step. Right, so I know that the printf works. We get this printf. Now the best I can do is just break at a couple different places, like 735, B, let's see, 735, and continue. And that worked. We did not crash in that loop. Now I just can go forward. Whoa. Page deck ref. Oh, page to pay, I see. Ref and status. Okay, we finished this. So now end free. And now we go into scheduled. And that's probably... So if I just do a next, that's where the crash is going to be. Okay, that's where the crash was. So now I can try this one more time. And free. Once, twice. Schedule. Yield. Now I'm in... Ooh, piece. Oops, shit. Okay. Once, twice, break, sched, yield, continue. So now the crash is going to be somewhere in here. And where, like, yeah, what might that be from? Oh. Okay, it's because we're going to... We couldn't... There's no runnable environments. I see. And so usually if that's the case, we halt and hit here. Okay, but yeah, now I've commented that out, and so this is going to weirdly return back to the caller, and I don't know, wreak havoc somehow, because there's just nothing for the kernel to do, and it's just going to, I don't know, it's just going to, I think, yeah, there's just nothing for the kernel to do, and we're like just blasting forward, so it makes sense that there would be a crash. Okay, so stupid idea to totally disable that for everything. I don't hear no buzzing. Sick. Okay, cool. Gotta remember that the speaker. Interesting how the speaker creates buzzing. Okay. Is there... Okay, so I'm like almost at the point where I'm going to give up at trying to make CPU1 participate in scheduling at this point. But... So really this like deadlock situation was kind of the issue. Maybe it's kind of the other way around. I mean, maybe I was being kind of stupid by not just thinking of this. but maybe it's really the other way around. So, oh shit, I deleted all the click lock stuff. Man, I should not have done that. Spin lock .h. Signed quick lock. And then we'll go into here. Equals 1. Okay. Quick lock. So it's going to first block on this. And what I need to do is I need to go to trap.c and set env runnable? No. Sys set env. Okay, why am I not finding it? Sys env set that. And I need to do the same thing. Exchange quick lock with a 0. And then now we need to go here, add the include, spin lock. Okay. Man. Let's try this. Okay, it didn't crash. I'm not seeing CPU 1 get anywhere. Okay, so the next step would be, this is like the final Hail Mary. Okay, did we get here? Oh, but wait a sec. No, I didn't enable multiple CPUs. Jesus. There we go. Okay, finally. Yeah, that is sick. So finally, we are actually using the multiple cores that are available and having them like run and get work. And now we will begin to see a bit more non-determinism, I think, in like this ordering. Whew. All right, that was a journey of being kind of dumb, but okay, cool. I mean, I'm not memorizing these orderings, but it's like 1 0 0 1 0 1. Well, it's not going to be the same thing next time. 0 1 0 0. So yeah, cool. So now that's awesome. Actually, it's like we spent all this time trying to get multi-core bring up working. That took forever. Now we have, but we weren't really using it for too much, I think. And now we finally have a couple of different tasks on the system. And we're finally seeing them actually get used. And interestingly, CPU 0 drops off and dies forever now, and CPU 1 takes over the rest of the work. So yeah, whew, cool. Thank you, Ismail. Thank you. I'm gonna call that a win. Dubs in the chat would be appreciated. Thank you. Sick. Okay, yeah, that was fun. I'm glad we were able to see that, and that just helps me kind of really have more confidence in my multi-core support and just seeing that work for the first time. We didn't make any process or progress on copy on write fork, really, because I got sidetracked with this observation that the other CPUs weren't actually used. But now that we have tried this, we can actually proceed more properly next time. And I'm also actually pretty stoked that this stupid little like quick lock thing worked, just using atomics. It's like this simple, like really bespoke lock, kind of like almost more like a condition variable kind of thing. I guess, yeah. And just a super simple use of an atomic. And how does it work? We just we create a global variable called 1, and it's just global because it's easy to access from everywhere in the code. Global quick lock variable. And on the CPU 1 side, so like the not main CPU, it's going to just be spinning. It's very important that it does that before it tries to acquire the kernel lock. It's super important that it happens before. And so before it even gets going with the main stuff, it's just trying to grab this quick lock, which is the thing that CPU 0 is going to use to indicate that we have set the new process, like the child process, to be in a runnable state. So now it is eligible for scheduling. And the way that works is we spin. It's a simple spin lock where basically this while loop is basically just trying to spin and wait for the point in time where that global variable transitions from 0 to 1. That's specifically what we're querying for here. We're trying to put a 1 in there, and we are also making sure that before we put the 1 in there, there was previously a 0, and this process happens atomically. And if the quick lock was still locked because it's initialized to 1, this thing is going to return 1, and so that's not the transition. Like that's just going to be us putting a 1 into an already 1 place. So there's no like 0 to 1 transition there. But then as soon as CPU 1 finishes this, sets everything up and sets the environment to runnable, it then sets that global variable to 0 atomically. And then the next iteration of the spin lock is now going to succeed because that variable is 0 now, and it tries to write a 1, and it observes this step transition and then proceeds with whatever it's doing. But after that point, we now have two processes that are ready to do work. And so now we're going to go and then do the normal waiting for the global kernel lock. So we're going to wait for the next time CPU 1 drops into user space and starts running code and releases the lock. Then CPU 1 can wake up, get the lock, inspect all the processes available for running. There's going to be 2 of them, but one of them will be used and actively running on CPU 1 or CPU 0. And so it'll grab the only remaining one and actually begin running it, which it was not able to do before. And then when everything's done, things just will hit that sched halt that I commented out, and they'll both gracefully reach the end. No runnable environments. So sick. Thanks, Ismail, for being here. Is a lot like a mutex? Yeah, like lock and mutex are kind of interchangeable. This quick lock thing is a little bit, it's not exactly a lock. I would say it's a bit closer to a condition variable. A condition variable is a thing where it's where you have different threads or concurrent processes running, and you have one thread that you want to just simply wait until another thread can do something and then signal that the first one should keep going, which is a bit of a different semantics than a mutex, which is for kind of blocking off a critical section. A condition variable is more for just kind of like signaling from different concurrent threads. And so actually a better name would be like quick condition variable or something like that. But yeah, I'm about to do first multi-threading soon. Don't know a lot about stuff. Yeah, I mean, yeah. It's like, yeah, it can be pretty challenging to think of like the interleaving and stuff, but it's also pretty rewarding. And I learned a lot about this from this book I like called The Little Book of Semaphores. That's how I actually learned this when I was first starting out, trying to learn about concurrency and stuff. And I have that book on my resources website too. But yeah, cool. I'm going to bring the stream to an end. Thanks very much for watching. I'll do my usual self-promotion. I have a Discord server. Feel free to join it if you want to keep in touch. Please subscribe to my channel and like this video and leave a comment if you like what I'm doing. And I do this every week. I'll be back next week and I will see you then. All right. Have a nice one. Bye.